we are discussing about recovering structure of from the set of corresponding pairs of points of a stereo system, and we have discussed how there are different approaches for computing that computing a scene point given a pair of corresponding point. So, just to illustrate this process, we will be discussing a problem for computing this scene point. So, consider this particular example that you have two camera matrices P and P prime for left and right cameras, and its images of a scene point are formed at say 0, 3.5 and 2 by 3 and minus 1 by 3. So, you have to compute the 3D coordinates of the scene point. You can see the projection matrices of the two cameras P and P prime, they are also given here. So, we will discuss the solution. So, let us consider how we are going to compute this particular to get the scene point. So, you have projection matrices P and P prime. I have shown in a very generic form. P is given by the elements submatrix capital M M, and the other one is given by M prime small m prime P prime. And we have shown that pairs of corresponding point as x and x prime. So, we will be applying the geometry approach of triangulation. That means, we will form the rays, back projection rays for these two cameras, and then try to compute its intersection. And due to the noisy observation, you will not exactly get that intersection of this. It is expected they should intersect, but you will not get exact intersections. So, what you need to find out a very close estimate of the intersecting point. So, you should consider a perpendicular segment for both the lines and then get the midpoint. That was the solution. So, let us see how this computation proceeds. So, C is the center of the first camera, C prime is the center of the second camera, and we can compute the direction cosine of the projection ray given the image point x. Similarly, direction cosine of the projection ray of the second camera given the image point x prime. So, this is what? So, minus m inverse m, that would be the center C, then minus m prime inverse m prime, that would be the center of the second camera, minus m inverse x is the direction cosine of the projection ray of the first camera, and minus m inverse m prime inverse x prime is the direction cosine of the second camera. So, with these computations you get to know all the three dimensional constructs of the straight lines, because you know the points passing through the straight line and you know its direction cosines. Now, you apply the three dimensional coordinate geometry to solve the perpendicular segment and its midpoint. So, there lies the solution. So, one of the property of this perpendicular segment, that its direction cosine should be obtained by the cross product of dx and dx prime, because it is perpendicular to that. And if I assume a point lying on the projection ray passing through the image point x and c as c plus s dx. So, s is it is a parametric representation of that straight line. Any point can be represented. S varies, s is any positive value. Similarly, c prime plus t dx prime is another point. So, what we need to find out exactly that which s and t will satisfy this constraint that the line joining them line joining those 2 points given by these values of s and t will give me a perpendicular directions of both the rays. So, that we translate. So, it is perpendicular to this, and then we need to solve for s and t applying this constraint. So, these are the computational steps. So, what we discussed, and here is the summary of all those results. As you can see that we have computed the first centers, this is given by this by applying these relations. Then you have computed the direction cosines by applying this particular facts. Then this is the direction of the perpendicular segment which is perpendicular to both of these rays, and then we are trying to solve for, we will be solving for s and t by applying the constraint that the line forms by this so the line forms by them this segment, it is perpendicular to both the directions of dx and dy prime. So, you get actually two equations. So, if you note the direction cosine of if you note the direction cosine of dx, that is 0.32, 0.47, 0.69, then in this slide you can see that you have taken the dot product of that direction with this particular expression, that should be equal to 0. Similarly, for from the direction cosine of dx prime, it should be orthogonal to this direction. So, the dot product of between these two vectors should be equal to 0. So, this gives me two equations. These are linear equations in terms of s and t. So, if you solve, and you can get s and t at the point. So, this is how we can solve this problem, and we can get the structure. Let us consider the other problem of line reconstruction. So, you consider here a particular situation where you have been given a straight line L, and you can get its two images, which will be again straight lines in the first plane, image plane, and in the second image plane. Incidentally, as you can see that they will be also an epipolar lines, those corresponding epipolar lines. So, this is a image of 3-dimensional line in the first image plane. Similarly, the image of the same line in the second image plane, both are given by L and L prime. So, what we can do here, that now given this line and given this projection matrix P, we know that equation of this plane is P transpose L. So, this is the equation of this plane. So, if I write say pi equation of this plane, so this is equation of this plane. Similarly, equation of this plane is P prime transpose L prime. So, now you have these two plane, one is say pi, another is say pi prime. So, when two planes intersect, they forms a line, and that is the solution, that is a 3-dimensional line, and that is exactly you will get if you compute this intersection. So, this is what I just mentioned. So, finally, your solution is in this form. So, this is one convenient way of representing a 3-dimensional line. Now, we will be discussing a very important property of a stereo system, an important feature of a stereo system, and you can show that how the projective transformations even among the image points they exist in a stereo geometry. So, the homography or the projective transformation those are established among the pair of corresponding points for which the scene points lie on a particular plane. So, we call this kind of homography is a plane induced homography. So, take this particular scenario which has been shown in this diagram, that you have once again two cameras of projection matrices P and P prime. So, P is given by I 0, that is the projection matrix for the first camera, and P prime given in this representation capital A and small a. Instead of m small m, we are using capital A small a in this particular representation. And we have a plane which is given by this algebraic representation. As you can see, this is the equation of a plane. So, representation of a plane in the homogeneous coordinate system of a 3-dimensional projective space. So, this is a vector, 3 vector, which is giving you the directions, cosines of the plane, and your scale value is kept as 1, which means the equation of the plane, if V is given as a column vector V1, V2, say V3, then the equation of the plane is V1 x plus V2 y plus V3 z plus 1, that is equal to 0. So, that is the equation of the plane. Consider a point on that plane which is given here x pi and its corresponding image points x and x prime. So, we can show that there exists a homography between these 2 points. So, you can take another points, for example, and also you can form its say images, say this is y and say this is y prime. So, this is the corresponding point. So, there exists a homography H such that H x will give me x prime and H y will give me y prime, and this homography is called plane induced homography. We can show these things. So, let us check the derivations, clean this particular diagram. So, we can see that we have already discussed earlier also that points in a plane and its corresponding image points in a single view camera also, they are related by a homography, because points in a plane can be represented by a 3 vector by 2 independent parameters, and they are related by a homography. Consider that homography is h1 pi. Similarly, you can have an homography h2 pi. So, from there you can get a homography which is given by this h2 pi, h1 pi inverse. This plane induced homography can be related with the parameters of the plane which is inducing this homography, and also the parameters of the projection matrices. So, here we have shown a proof that how it is related. The basic theorem is that this homography is given by this. That means, plane induced homography can be expressed in this form, where A is the 3 cross 3 submatrix of the projection matrix of the second camera or P prime, and this vector small a is the fourth column vector of this projection matrix, and V, as you know, this is the direction ratios of the normal of the plane pi. So, this has been shown here how it can be related like this. So, let me just provide you the outline of this proof as it is given here. As you can see that x prime, which is the image of the scene point x, is given by this P prime x, which is can be expressed in this form, whereas x is just P x, which can be expressed in this form. So, now any point in this ray can be considered as x rho. As you know that in the homogeneous coordinate system, the scale factor provides you the corresponding points and the interpretations with respect to 3-dimensional space. Real space is that it could be any point in that projected ray connecting the image point x. You should note that at rho equal to 1, you have the image point. So, when rho is 1, this is represented in this form, and when at infinity, this would be represented in this form x 0. So, exactly at what value of rho you are getting this value x, that can be determined by considering the point containment relationships on the plane. So, if I take pi transpose x rho, this vector, that should be equal to 0, and value of rho is given by minus v transpose x, and that now we will be using in the expression of x prime. So, now x is related with this capital X, that is the scene point, is related with the image point x, and also the corresponding scale factor which has been computed using this particular fact of plane point containment in plane. So, x and scale factor is minus v transpose x. So, if I do the corresponding submatrix multiplication, I will get it as A x minus A v transpose x, and so this can be written in this form. So, as you see, x prime is related with x by this linear transformation, and which is nothing but we call it a projective transformation, and which is what is homography H. So, you get in this way, this is the direct relationships. So, using this particular fact, we can say that a transformation H between two stereo image is plane induced homography if you can say in the other way that a fundamental matrix can be decomposed into this form. We know E prime cross H. E prime is the epipolar plane, epipoles, right epipoles, and as you know that the cross product of right epipole with the matrix, that is an operation, matrix operation. Basically, this E prime cross is a matrix, equivalent matrix which is representing that operation. That itself will be will give you F. We have discussed that actually this homography, it could be any homography, and that is what it is represented here. Previously, we have taken only the homography at plane at infinity. So, even if I decompose F in this form of E prime cross H, if we decompose F in this form of E prime cross H, then P and P prime can be obtained, can be expressed in this form. It is a in the family of pairs of projection matrices, this could be also one such option. So, we can also say that if you have two projection matrices P, which is in the canonical form of I 0, and P prime, which is given in this form, as we can see that a plane induced homography H, and then the plane can be recovered by solving these equations, because we know that homography would be we have seen that homography is given by A minus A v transpose in the previous case, but naturally this equality we cannot establish unless we know what is the exact equality can be determined, can be put when we know exactly at what scale this equality holds. So, that is why we have to rewrite this equation in this form. So, what are the unknowns here? There you have the unknown k and unknown v. So, there are you get a linear equations. There will be there in the H there are 8 elements, 8 independent elements, independent parameters. So, you can get linear equations for unknowns k and v, and that you can solve using this homography. So, this is how you can get the equation of a plane. Another feature of the stereogeometry that this plane induced homography, or you can find out whether it is compatible to a fundamental matrix or not. Like you have observed, you have discussed how fundamental compatibility of fundamental matrix with pairs of projection matrices could be tested by observing whether it is that there is a skew symmetric matrix property P prime transpose F P should be skew symmetric. Similarly, here also you can see that H transpose F should be skew symmetric. So, that is that is one of the interesting property, that is one of the feature of the skew symmetric matrix, as the transpose of that matrix is a negation of the matrix. So, if we add the transpose, you should get 0. So, this can be shown in this form, that is a proof that since x prime transpose f x equals 0 and x prime is h x. So, h x transpose f x equals 0, and this is true, once again this is true for every x, because see these are all same image point. So, this is true for every x. So, H transpose F is a skew symmetric matrix from the property of a skew symmetric matrix. So, these are certain facts of the stereogeometry, that once you have a plane induced homography, that means in this case the corresponding pairs of points, they are all formed from the scene points of a plane. So, that is explained by that form. So, you consider a plane, any plane you consider, and in that plane, if it is not parallel to the baseline, there is an intersection with respect to that plane. So, once again, if for that plane, if there is a homography H, so E prime should be equal to H E for that plane induced homography. Similarly, we have mentioned that epipolar lines, corresponding epipolar lines which are lying on the same epipolar plane, and any particular line lying on the same epipolar plane, which they also form the plane induced homography, because once again the plane which is inducing and points are lying in that plane, and any intersection of that plane with respect to epipolar plane will satisfy this constraint. So, this is also satisfied for any pair of epipolar lines, this is satisfied. And H x lies on epipolar line of L E prime. That is another constraint, it has been shown that here also you can see that if you have a scene point, if you have some scene point here, this is epipolar line. So, epipolar line of a corresponding point can be obtained by performing the multiplication with respect to x f x, and then that means I can obtain the epipolar line by multiplying x, and if I perform the homography transformation on x, so this point will also lie here. That means I can write H x transpose f x, that should be also equal to 0. So, that is the essence of this particular computation. So, we will be considering, we will be exploiting these facts for estimating the fundamental matrix under certain constraint scenarios, because that would simplify the computations. Suppose you would like to compute fundamental matrix from 6 points, out of which 4 are coplanar. So, I can, using that 4 coplanar points, we know that they establish a homography. So, their corresponding points, there is a relationship of homography among themselves. So, you can compute the homography matrix H pi using those 4 points, and then you can find out the epipoles by computing the epipolar line. So, that means you consider the actual corresponding points which has been observed for x 5. So, you have x 5 corresponding to x 5 prime, then x 6 corresponding to x 6 prime. Also, you had x 1 corresponds to x 1 prime to x 4 corresponds to x 4 prime. So, first you compute the plane induced homography among themselves. You require minimum 4 point correspondences. So, now if I transform x 5 using this homography, the same point will lie in the epipolar line f x 5, or I should say the epipolar line will be formed because f is not known. So, epipolar line will be formed by h x 5 cross x 5 prime. So, that is what is shown x 5 prime, and this is the plane induced homography point. So, they will form an epipolar line. In the same way, using the other point you form the second epipolar line. So, you will get another point. So, you get x 6 prime and it is suppose this is x 6, this is x 6. It may be somewhere else, it is not here. So, this point may be here, and say this is x 6 prime, and after homography transformation this is h x 6. So, this will also form another epipolar line. So, these two epipolar line L 1 and L 2, their intersection will be E prime, that is expressed in this form. So, if I take the cross product of L 1 and L 2, I will get E prime. So, now fundamental matrix can be defined as E prime cross H prime, that is fundamental matrix. So, you can compute it. So, using this 6 point fundamental matrix from 6 points, you can compute using these 6 points you can compute fundamental matrix. Now, here the problem is in the reverse. You have been given a fundamental matrix and 3 point correspondences, and then you need to compute H. So, the first method says you can fundamental matrix, you can always estimate the camera matrices P and P prime using the method what we discussed, and then you can obtain the plane because you have 3 scene points and you solve for the 3 scene points, construct 3 scene points and obtain the plane, and then from there you can compute the plane induced homography, that is H equals A minus A V transpose given the parameter in this form. The second method is that for that 3 point correspondences you require another point correspondences from which you can get this homography, because minimum 4 point correspondences are required. So, what are those, what is that pair of point correspondences? That is the epipoles. So, from F you can compute these epipoles, that means you get its left 0 and right 0, those are the epipoles and they are also corresponding points. So, now you have 4 corresponding points, from there you can compute homography. So, this is also another interesting feature that any 3 points can bipartition the image space with respect to the plane formed by them. Infinite homography we discussed earlier also, and let us discuss it in the context of this plane induced homography. So, you consider any general plane induced homography, which is the results are shown here at the top. Here you can see that this is the general result of homography given your projection matrices in this form and also the plane, 3-dimensional plane, the representation in this form. So, in this case of course, this is given in the form of ND. So, that we can relate it. So, if you just scale this normal vector by D, that is equal to B. So, let us see how this. So, now your plane induced homography following this particular construct could be written in this form. Now, here your projection matrices are given in this. So, it is related with A is K prime R. So, this is A, and your E prime is given by this, no, E prime is the image of this coordinate, which is 0, center is at, since it is 0, center is at 0 0 at the origin. So, if I take the image here, and you will get the corresponding, so it is T. So, the epipole is image is at T, right. So, this E prime we will find out, E prime will be T, and let us see what is K inverse. K inverse, because this is I 0, so K inverse will come here. So, we can make it in a canonical form if I transform the image coordinate by K inverse. So, these are the things. So, V should be equal to N D, and E prime is K prime T, E prime is K prime T from here. So, that is what is E prime, and then H pi following this formulation can be written in this form. So, you note that V is given this N D. So, it is T N transpose D R. So, finally, it is K prime R K inverse minus this. So, now as D tends to infinity, H infinity is K prime R K inverse. This is a form which we discussed earlier also, that is the homography at infinity can be expressed in terms of these camera parameters. And we discussed also earlier how in general configuration, how the corresponding pairs of points are related with this particular parameter. So, this is what we get using infinite homography. So, as Z tends to infinity, x prime is the image of point on pi infinity. So, this shows you that is the vanishing point over the epipolar line as you are projecting the points at infinities. So, this is a summary between the line the homography at infinity and vanishing points H infinity. It maps vanishing points between two images, and it can be computed by identifying 3 non-collinear vanishing points given F or from 4 vanishing points. So, we discussed earlier also that given 3 points and fundamental matrix, you can compute the homography. So, if you have vanishing points and corresponding vanishing points, you can compute H infinity in that case, or you can get 4 pair of vanishing points, you can compute H infinity. And if your camera matrices are given in this form, P and P prime, and any point at infinity is given in this form, we discussed earlier also, this shows that H infinity is M prime M inverse. This relationship we discussed while solving a problem itself, that given a general camera representation, how homography at infinity or plane induced homography when the plane at infinity is the inducing plane is expressed in this form, or H infinity is M prime M inverse. So, with this let me stop this lecture at this point. We will be continuing our discussion on stereogeometry in also subsequent lectures. Thank you very much.